Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is minimum number of vertices to reach all nodes. So let's go to LeetCode. Alright, so given a DAG, directed acyclic graph with n vertices numbered from 0 to n minus 1 and an array given edges, where edges, basically the ith position represents two value a and b from to, so there is an edge going from this first node and to the second node, so from to. It represents a directed edge from node to node 2. The most weird description I have ever read. You could just simply say like a and b, that's the pair, and there is an edge going from a to b, that's it. Trying to be extra smart here. Well, anyway, find the smallest set of vertices from which all nodes in graph are reachable. It's guaranteed that a unique solution exists. That means there are no cycles. That you should like comprehend yourself, because that's the only case like where there will be a unique answer, right? Okay, notice that you can return the vertices in any order. All right, so let's consider our first example. Okay, so I have taken the first example right here. We are given n nodes, so there will be nodes from 0 to n minus 1, which is 5. So there are 6 nodes right here, and then we are given these nodes and these connection. It's acyclic, directed acyclic graph. So these are the edges. Here it represents from and to. So this is a and b. There is an edge going from a to b. Now tell me here, okay, by the way, this 0 is connected to 1, 0 is connected to 2, and then 3 is connected to 4, and 2 is connected to 5, and 4 is connected to 2. So this is our entire graph. Now we need to find the minimum number of nodes using which we can traverse the entire graph. That is the summary that has been asked to us, which was find the smallest set of vertices from which all other vertices or nodes are reachable. So tell me, the nodes that already have incoming edges from other nodes, they do not have to be in that set, right? Because they can be visited from some other nodes. It's only the nodes that do not have any incoming edges, right? Because this doesn't have any incoming edges, so it cannot be reachable from some other node. That is why these have to be in our set. If we're creating some set, they have to be in our set. So for example, 0 does not have any incoming edges, 3 does not have any incoming edges. So from 3 I can go to 4, from 4 I can go to 2. So this one group is traversal, or from 2 to I can go to 5. All right, but then there is another group left, which is from 0 to 1. Now I can reach all the nodes. So either this and this, or it could be just these and these two together. So we have to have these two nodes 0 and 3 in our answer for this particular problem. But if you see clearly, it's only the nodes that do not have any incoming edges. That's what we need. So what we'll do is we will use edges to create our graph adjacency list. So we'll call it graph, and this will have basically all the nodes 0, 1, 2, 3, 4, and 5 as keys, and then next to them we will be appending all the incoming edges that are coming from the nodes. So basically these are the nodes, and next to them we will have the nodes that are sending an incoming or outgoing edge to 0. So let's say 0, what is the incoming edge that's coming from coming to 0? Well, there is not. Remember, this is like we are doing it in a reverse way, because I want to basically find out the nodes that do not have any incoming edges. So it's not about outgoing edges, it's the incoming edges. So 0 does not have any incoming edges. How about 1? 1 does have an incoming edge, that is from 0. How about 2? Yes, it has 0 and 4. How about 3? 3 also does not have anything. How about 4? 4 has from 3, 5 has from 2. And 2 has from 0 and 4. So in this graph right here, how many nodes do not have anything in their list? Well, these are the 2 nodes and these are our answer. So because rest everything else will be reachable from some other node, because they do have some neighbors sending an incoming edge to them. So there is an edge coming to these other nodes from some of their neighbors. So that is why they do not need to be in that minimum set. All right. So I think it's going to be super simple. What we can do is just create this adjacency graph. We have done it like so many times. Just like one really like, small tweak that we will be making. Can you see my face? Let me turn the lights on. Whoa, 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 whoa. All right, so let's create this graph adjacency list. Initially it's going to be default dict of list. Let's go over A and B and let's call it source and destination in edges. So here in my graph I will be adding to the destination I will be appending the source, because from source there is an edge going to destination. So destination should be reachable from source. It's the source that we need to actually collect into our graph, and simply we can create our answer. It's going to be super simple. So for node in range n, if this node, I would say if this node here in this graph, if this node, we can say graph and this key does not exist, or its length is equals to 0. So I would say this node's length is 0. Should have been simple. I should have I don't know, I just complicated it, but anyway. Then we will append that to my answer. Okay, so that would be node, and then finally we can just return our answer. All right, so let's run it on the examples, and I'm gonna zoom out. Okay, so range n, node in range n. Sorry about that. I had a long day. Yeah, I'm shooting these videos like at the end of the day, and it's already like fucking tiring. So that is why I'm making those typos. That's not an excuse. That is an excuse. Sorry. But let's write down the time complexity. Complexity is going to be, we are visiting basically all the nodes, so it's going to be n. We're not doing anything else, right? Going over all the edges. So you could say, we could say it could be v plus e, going over all the nodes and edges. And for space complexity, we are storing a graph, so that is also going to be big of v plus e. But you can definitely bring this down to just number of vertices, because in this graph I'm creating the dictionary, but you don't have to. You can create like an array of size n, and at each of those nodes you can, like, if you see at that particular destination index, if this index being a destination, if there is some value present, so there is some value coming from source, so on all the destination basically you can increment some values and then go over that array, and wherever the value is 0, that's where you actually add those to your answer. Well, anyway, this is also pretty good, accepted. Let's mark this solved. See you guys later. Bye bye.